The Hubble Space Telescope is probably the most famous facility in astronomy. Almost everyone knows about it or has seen the beautiful images, and many of you probably have them on your computer as screensavers. Hubble Space Telescope is a NASA facility jointly operated with the European Space Agency. And in general, 85% of the time on the telescope goes to American or US-based astronomers, while 15% goes to European astronomers. But anyone in the world can apply for time on this incredible facility. It's open to all. There's even a small amount of time every year that's given to teachers or amateur astronomers by competitive peer-reviewed process. The Hubble is an orbiting telescope that collects light from celestial objects at optical, near-infrared, and ultraviolet wavelengths. It was launched in April 1990 aboard the Space Shuttle Discovery. It's a 2.4-meter mirror telescope. It weighs about 5 tons, and it was designed to fit inside the Space Shuttle bay, and in fact is the largest telescope that could have been launched by the Space Shuttle. As a Space Shuttle launched instrument, it's in a low Earth orbit, roughly 250 miles straight up. Earth orbit is not that far. That's about as far as you could drive in an afternoon, only straight up. Its orbital period is 90 minutes. And for a small fraction of that orbit, it passes through a region called the South Atlantic Anomaly, where the radiation and magnetic fields in the Earth environment are sufficiently severe that observations are compromised. Typically in a 90-minute orbit, Hubble takes data for about half of that time. It's a very efficient telescope, however. Its observing programs are scheduled by an artificial intelligence algorithm. Humans would not be smart enough to schedule thousands of telescope proposals amongst hundreds of different ways the instruments on Hubble can be used. The telescope is operated out of a science institute called the Space Telescope Science Institute, located in Baltimore, just outside Washington. And it's named, of course, after Edwin Powell Hubble, the discoverer of the expanding universe and the extragalactic nature of galaxies. Hubble is a magnificent facility, but it didn't start so well. Those of you with long memories may remember the first images from the Hubble Space Telescope. They were not very impressive. Basically, all the point sources that should have been completely sharp, with imaging above the Earth's atmosphere, were blurred out. Actually, they did have central cores, but they sat on a low plateau of light that was spread over 10 times the radius or angular diameter that it should have been. Hubble was producing blurry images. But it wasn't because the optics were poor or imprecise. Rather, it was because the mirror was made precisely wrong. We'll talk about how that was fixed in a minute, but meanwhile, it was a public relations disaster for NASA in 1990. They had, of course, talked up this facility, which was very expensive, enormously ahead of the mission, so people were full of anticipation. When the first images came, the cartoonists got going, David Letterman issued a top 10 excuses for the Hubble Space Telescope, and really NASA became the laughingstock for a short period of time. It was an ignominious start for astronomy's premier facility. However, NASA was able to snatch victory from the jaws of defeat with an audacious fix to the telescope that went up on the first Hubble servicing mission a few years later. The instrument that was installed was called COSTAR, and essentially it was eyeglasses applied in front of each of the instruments on the telescope to restore perfect vision. To see how COSTAR works, we have to know why Hubble was wrong and how it was built wrong. Like I said, the mirror was not imperfect or imprecise, it was precisely built to the wrong specification. What happened was, in a final calibration sequence, one corrective element was misplaced by literally less than a millimeter. And that led the final figure of the mirror to be created precisely wrong. This means, of course, that Hubble could be corrected with suitable eyeglasses, which was indeed the fix that was settled upon. The disaster for NASA was that this cost a lot of money and should have been avoided in the first place. NASA learned painful lessons through this process. They learned that by saving $30 million on a final test of the entire optical telescope assembly, they cost themselves close to $500 million in fixing Hubble. They changed their management procedures and never again launched a space telescope without fully testing it on the ground first. The pictures of the point source before and after the COSTAR fix show how perfectly COSTAR worked. Essentially, these eyeglasses, or corrective lenses applied in front of each of the Hubble instruments, restored Hubble's perfect vision. At the time, it was indeed the best mirror ever made, and with these fixes, once again, it's the best mirror ever made. The key with CoStar and with fixing Hubble is that Hubble is in a low Earth orbit. And the low Earth orbit meant that Hubble could be serviced by the same space shuttle that launched it in the first place. Astronauts fixing the Hubble, or upgrading its instruments, which has now happened a total of 5 times, perform perhaps the most difficult tasks ever performed by humans in space. Astronauts out of the Johnson Space Center fight each other to be on the Hubble servicing missions because they are so challenging. They involve spacewalks, use of difficult instruments in the vacuum environment of space, enormous time pressure, and an exhausting schedule in a 10-day shuttle flight, where each astronaut may have 5 extravehicular activities or spacewalks. One man, John Grunsfeld, who's now Deputy Administrator of the entire NASA organization, was involved in 3 of the Hubble servicing fixes. He's a hero to astronomers because he not only fixed the telescope in the first place, but went on 2 of the servicing missions that changed instruments. Hubble is well into its 3rd decade, and it remains a premier instrument for astronomy because of the servicing missions. Every 3 or 4 years throughout its history, the shuttle has gone up with new instruments to improve its capabilities.
I'm Kathy Thornton. I was a mission specialist on the first service mission on Hubble Space Telescope in 1993. It's amazing to me when I was flying in space, orbiting, that I can look back at the Earth and you don't see a lot of evidence that we're here. But yet, those little tiny beings down on Earth that I can't see were smart enough to get me there.
And then I'm going to pull it a little bit and we'll just communicate.
We were not the most significant part. We might have been the most visible. But the real heroes of the service missions are the people who figure out how to do it. The people who came up with the fixes.
Probably use the existing MLI, come up with some type of cover that we will put on it and tape it in place.
My name is Russ Warneth. I've been involved with all 5 of the Hubble servicing missions. Back in 1993, when we did our first servicing mission, I was involved in designing all the tools that we use.
On that mission, we did 5 spacewalks. I did the 2nd and the 4th one. On my spacewalks, we put in new solar arrays, and we installed the CoStar, which included the corrective optics for all the axial instruments in the bottom part of the telescope. We think a lot about the engineering and the technology that goes into Hubble and makes it work, and the innovation and design that went into the fixes for the Hubble and every new instrument that goes up in the Hubble. And those are pretty amazing. But the purpose of the Hubble is science. The purpose of Hubble is to help us learn about where we came from, about what happened before us in this universe. Servicing the Hubble one more time with the shuttle is well worth the risk to the crew and to the vehicle and to the Hubble itself. Every time we touch it, you know, we plan to make it better, but you could always make it worse. And so there is some risk to the telescope as well.
When we plan for a servicing mission with the astronauts, we always ask ourselves the questions, what if? What if this tool were to fail? What if this procedure wouldn't work? And therefore, we do all the training that's necessary. We have contingency tools. We have backup tools. We have backup procedures. There was a handrail that had to be removed. And as much as we practiced on the ground with tools and procedures, that handrail couldn't be removed because of one of the bolts. As Mike Massimino was working real time with his EVA, his spacewalk, we were working on the ground to figure out how we could solve that problem. And we went through several levels of contingency. And then ultimately, it came down to just using brute force on that handrail to get that bolt to break. And we've essentially been able to leave a new telescope every time we finish up a servicing mission.
I have a picture on my wall of one of the first Hubble Deep Field photos, where Hubble was pointed at a place in the sky where there wasn't anything. But imagine that you could look through a straw or a pinhole and find a place in the sky where there's absolutely nothing, and know that there are millions of galaxies in that little pinhole that you're looking at. I think more than anything else, Hubble is an icon of science, of exploration, and of the things that we as humans can do.
Hubble is a great observatory-class mission of NASA, which means it's a general-purpose facility that works on everything from comets to cosmology and has typically 3 to 5 different instruments with different capabilities working in parallel. Observations are sequenced between the instruments to answer a whole series of astronomical questions. Hubble has made important impacts on almost every subfield of astronomy, and throughout this course we'll be hearing about results where Hubble had its hand. Among the research topics where Hubble's made an enormous impact was the measurement of the current size and expansion rate and age of the universe, the discovery of a diffuse intergalactic medium that contains as many normal particles as are contained in all the stars and galaxies in the universe, characterization of extrasolar planets and protoplanetary disks, the use of supernovae to measure the accelerating expansion of the universe, and extraordinary work drilling down into the regions where stars form and also where stars die to learn about those transient phases of stellar evolution. Hubble also made a huge impact discovery that every galaxy in the universe has a supermassive black hole, our own galaxy included, and the mass of those black holes scales with the number of old stars in the galaxy. What does it mean to look 10 billion times fainter than the eye can see, which is the limit of the Hubble Space Telescope? If we look at this familiar piece of sky, where the Big Dipper is outlined as a constellation visible to the naked eye, and then zoom in stages, first to the depth visible through binoculars or a very small telescope, then to the depth visible through a 1-meter telescope that professionals might use, then to a 4-meter medium-sized telescope, finally to the depth of the Hubble Space Telescope, itself a relatively small telescope. We see, zooming in, we're looking at successively smaller and smaller scales. Hubble's CCDs only cover or mosaic a very small region of sky, much smaller than the diameter of the full moon on the sky. But they go with extraordinary depth, essentially plunging a pencil beam or wedge through the universe to enormous distances, perhaps 10 or 11 billion light years. In the final field at the end of these series of zooms, every smudge of light you see is a distant galaxy. The brightest of them may be 2 or 3 billion light years away, the faintest 10 or 11 billion light years away, almost at the dawn of time and looking back 90% of the time since the Big Bang. A telescope with this capability does not, nor did it come cheap. Hubble's original price tag before launch was spec'd to be about $500 million. However, by the time of launch, delays and cost overruns had ballooned that to $1.5 billion. It's actually hard to estimate now, after 23 or 24 years, how much Hubble has cost. Some of this depends on whether you factor in the cost of the servicing missions run out of Johnson Space Center. Those are probably $500 million each. The shuttle didn't come cheap either. Either way, the cost of the Hubble to date is somewhere between $6 and $8 billion. An extraordinary price tag for extraordinary science. By the numbers, Hubble is extraordinarily successful. It's made hundreds of thousands of observations and led to the publication of tens of thousands of papers. By any metric, it is the most successful science mission ever, in any field. It also led to the work that resulted in a Nobel Prize in Physics just last year. After 4 servicing missions and over 20 years of operation, the Hubble Space Telescope was scheduled to die a natural death. Among the things that are fixed when the servicing missions go up are the solar panels, which provide the vital energy from the sun, and various battery packs and other mechanisms by which Hubble powers its instruments. Other critical ingredients in the Hubble Space Telescope are the gyroscopes. Any telescope needs 2 gyros as a minimum for pointing on the sky. 3 provide brilliant precision, and the 4th is a redundant gyroscope. All through the mission, Hubble's gyros were failing at a rate that was unanticipated and was higher than similar gyros on the ground showed. So almost every Hubble servicing mission has involved swapping out the gyros. When Hubble loses 2 out of its 4 gyros, it is severely hampered. When it loses the third, just by natural causes, it will be essentially dead in the water, unable to point at any particular area of the sky. This is the most likely way that Hubble will die. After the 4th servicing mission, however, there had been 2 losses of the space shuttle. NASA's chief administrator was reluctant to fix the Hubble one more time because of the risk to the astronauts. It didn't really matter to him that the astronauts sign up for the risk and actually clamored to fix the telescope. No, the administrator decided it was too risky and that Hubble should die a perhaps early natural death. What happened then was very interesting, and you may have heard of it or even been a part of it. NASA's mailbag and emails filled with commentaries and comments and questions and complaints from everyone from kindergartners to retired people. All of these people knew what Hubble had done and found it unconscionable that NASA was going to let the telescope die ahead of its time. The common refrain in these communications was, "It's our Hubble. You have to fix our Hubble. Save our Hubble." The possessive term indicated that the pretty pictures were more than that the public, the country, had taken the Hubble into its heart and had some sense of ownership of it. In a very interesting progression over the next 12 months, the NASA administrator reversed path, changed his mind completely, and allowed the Hubble to be serviced one more time by astronauts, which happened a couple of years ago. But that was the last that ever was going to be scheduled. So when Hubble eventually runs out of either solar power or gyroscopic pointing, it will die a natural death after a long and glorious mission. So the Hubble Space Telescope is not the only space telescope available to astronomers, but it's their preeminent facility. In its long and illustrious career, it has pushed back the frontiers of numerous astronomical topics. It's taken spectacular images that grace the walls of schools and museums and planetaria and adorn many people's computer screens. Hubble Space Telescope is an incredibly expensive and exquisitely precise facility that has transformed astronomy.